Welcome to G Fun Facts Online. Today, we are going to tell a story about vision. It is a story that begins in the mud of the ocean floor, specifically in the eyes of a creature that has been crawling through the sediment for hundreds of millions of years. It ends in the vacuum of space, looking at the most violent explosions in the universe. This is the story of how the spiny lobster taught astronomers how to hunt for black holes. To understand why this is such a significant breakthrough, we have to start with the environment of the spiny lobster, or Penularis argus. This creature lives in the deep, murky waters where light is a luxury. In the animal kingdom, most eyes, including yours and mine, work on the principle of refraction. We have a curved lens at the front of our eye. When light hits that lens, it bends, focusing down onto a single point on the retina. That works beautifully for visible light. But the lobster faced a different evolutionary pressure. It needed to detect motion in dim conditions across a massive field of view. Evolution didn't give it a lens, it gave it a mirror. The lobster's eye is a honeycomb of thousands of tiny square-shaped tubes. Unlike the hexagonal eyes of a fly, these squares are lined with a reflective material. When light enters one of these tubes, it bounces off the internal flat walls, once off a vertical wall, once off a horizontal wall, and is funneled down to a central point. This geometry allows the lobster to see light coming from almost anywhere, concentrating it to create a bright image in a dark world. For a long time, this was just a biological curiosity. But in the late 20th century, astronomers were hitting a wall. They were trying to build telescopes to look at the universe, not in visible light, but in X-rays. And this is where the physics gets difficult. Building a telescope for visible light is relatively easy. You polish a glass mirror, coat it with silver or aluminum, and the light bounces right off. But X-rays are different. X-rays are high-energy photons. If you fire an X-ray at a standard bathroom mirror, it doesn't bounce, it acts like a bullet. It smashes right into the glass and gets absorbed, or it passes straight through. This is exactly why X-rays are used in medicine. They pass through your soft tissue to reveal your bones. But for an astronomer trying to catch X-rays from a dying star, this penetrating power is a nightmare. You cannot catch X-rays with a standard dish. The only way to reflect an X-ray is to trick it. You have to hit the mirror at an incredibly shallow angle, less than 1 or 2 degrees. Think of it like skipping a flat stone across a pond. If you throw the stone straight down into the water, it sinks. That is the X-ray hitting a mirror head-on. But if you throw the stone almost parallel to the surface, it skips. That is called grazing incidence optics. For the last 40 years, X-ray astronomy has relied on this skipping stone technique. The standard design, known as the Wolter Type 1 telescope, uses nested cylinders of mirrors. The X-rays enter the open end, graze off the sides, and focus at the back. This design, famously used by NASA's Chandra Observatory, creates incredibly sharp images. But there is a catch. Because the mirrors have to be long and shallow to catch those grazing rays, the telescope suffers from severe tunnel vision. The field of view is tiny, often covering a patch of sky smaller than the full moon. A Wolter telescope is like a high-powered sniper rifle. It is fantastic if you know exactly what you want to look at. If you want to study a specific black hole, it's perfect. But the universe is a dynamic, explosive place. Stars are detonating, black holes are shredding suns, and neutron stars are colliding all over the sky, at random times and in random directions. If you are looking through a sniper rifle, you will miss the explosion happening behind you. Astronomers didn't need a sniper rifle. They needed a surveillance camera. They needed a wide-angle lens that could watch the whole sky at once. This is where Roger Angell enters the story. Roger Angell is a renowned astronomer at the University of Arizona. In the late 1970s, he came across a biology paper describing the square eyes of Macruran crustaceans, lobsters, and shrimp. He realized that the lobster had solved the X-ray problem millions of years ago. In 1979, he published a landmark paper titled Lobster-Eyes as X-ray Telescopes. He proposed that if we could manufacture millions of tiny, square, hollow tubes and curve them into a sphere, just like the lobster's eye, we could create an X-ray lens with a field of view thousands of times larger than the sniper rifle telescopes. The geometry Angell proposed was elegant. In this design, X-rays entering the square pores would graze the sides, just like the stone skipping on the pond. But because the pores are arranged spherically, X-rays coming from any part of the sky would find a set of pores aligned correctly to reflect them. This creates a very specific focusing effect. Unlike a standard lens that creates a perfect dot, a lobster-eye optic creates a distinctive cross shape. Most of the light focuses into a central bright spot, but some rays only bounce once, creating cross arms. If you see an image of a star with a giant X through it, you are looking through a lobster eye. The theory was sound, but the engineering was impossible. In 1979, we simply did not have the technology to build millions of microscopic, perfectly square tubes, align them on a curve, and polish them to be smooth enough for X-rays. The idea sat on the shelf for nearly 30 years. It was a paper tiger, brilliant in theory, unbuildable in practice. The pores needed to be about 20 to 40 microns wide. That is roughly half the width of a human hair, and the walls had to be smoothed down to the nanometer scale. The breakthrough finally came from the night vision industry. Engineers had developed something called micro-channel plate technology. By the 2000s and 2010s, researchers at the University of Leicester in the UK and companies like Photonis in France figured out how to adapt this for astronomy. The process they developed is a feat of extreme material science. They start with a square rod of glass inserted into a square tube of a different, etchable glass. They draw these out into thin fibers, like making rock candy. They stack these fibers into bundles, draw them out again, and repeat the process until they have a solid block containing millions of microscopic glass fibers. Then they slice this block into thin wafers. They heat the wafers and slump them over a spherical mold to give them the curvature of a lobster-eye. Finally, they dip the wafers in acid. The acid eats away the core glass fibers, leaving behind millions of hollow square tubes. The last step is to coat the inside of these tubes with iridium or gold to make them reflective. After 40 years of waiting, humanity finally had the eye. Now, we had to prove it worked in space. The Chinese Academy of Sciences took the lead on this. In July 2022, they launched a mission called LEIA, the Lobster-Eye Imager for astronomy. It was a small technology demonstrator. The results were spectacular. LEIA captured wide-field X-ray images of the galactic center and the Cygnus Loop Nebula. The images showed that characteristic cross shape predicted by Roger Angel. The delicate glass pores had survived the violent vibrations of a rocket launch and the freezing vacuum of space. The test was a success. It was time for the main event. On January 9, 2024, a Long March 2C rocket roared into the sky carrying the Einstein Probe. This satellite is the realization of the Lobster-Eye dream. It is designed for what astronomers call time-domain astronomy, the study of things that change, flash, and explode. The Einstein Probe carries two instruments that work in perfect harmony. The first is the Wide Field X-ray Telescope, or WXT. This is the Lobster-Eye. It consists of 12 modules, each containing 36 million micropores. Its field of view is staggering. In a single shot, it covers 600 square degrees. To put that in perspective, that is roughly 1/11th of the entire celestial sphere. In just 3 orbits, about 5 hours, the Einstein Probe can scan almost the entire night sky. But the Lobster-Eye, while wide, doesn't have the highest resolution. It's the spotter, not the analyzer. That is why the probe carries a second instrument, the follow-up X-ray telescope, or FXT. This is a traditional Walter telescope, the sniper rifle. Here's how the hunt works. The Lobster-Eye scans the whole sky. Suddenly, it detects a flash, a new X-ray source that wasn't there an hour ago. The satellite's onboard computer calculates the coordinates and automatically slews, or turns, the satellite to point the sniper rifle at the target. The FXT then zooms in to analyze the spectrum and physics of the explosion. This combination of a wide-angle discoverer and a narrow-angle analyzer allows us to catch events in real time. So what exactly are we hunting with this new bionic eye? The primary targets are transients, events that are here one moment and gone the next. One of the most dramatic targets is the tidal disruption event, or TDE. This happens when an unlucky star wanders too close to a supermassive black hole at the center of a galaxy. As the star approaches, gravity pulls harder on the front of the star than the back. The star is ripped apart, a process technically known as spaghettification. The star is stretched into a long stream of hot gas that spirals into the black hole. As it falls in, it heats up to millions of degrees and releases a massive flare of X-rays. Before Lobster-Eye optics, finding a TDE was mostly luck. They are rare, happening once every 10 to 100,000 years per galaxy. But because the Einstein Probe watches thousands of galaxies simultaneously, we expect to find dozens or even hundreds of them a year, turning a rare curiosity into a standard dataset. Another major target is gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. These usually occur when a massive star collapses or two neutron stars collide. They emit a prompt flash of gamma rays, followed by an afterglow in X-rays that fades very quickly. Catching this afterglow is critical to pinpointing where the explosion happened so other telescopes can look at it. The Lobster-Eye's wide view ensures that when a burst goes off, there is a high probability the telescope is already looking at it. Perhaps the most elusive target is the supernova shock breakout. When a massive star dies, its core collapses, sending a shockwave racing outward through the star's layers. When that shockwave finally breaks through the surface, it produces a brilliant, blinding flash of X-rays. This is the very first signal of a supernova, but it lasts only minutes. By the time visible light telescopes see the supernova days later, this shock breakout is long gone. The Lobster-Eye telescope offers our best chance to witness the exact moment a star dies. The success of the Einstein Probe has kicked off a new era. It is not alone. In June 2024, a joint French and Chinese mission called SVOM was launched. It uses a Lobster-Eye telescope called MXT. In this case, they use the technology not just for the wide view, but because it is incredibly lightweight. Traditional mirrors are heavy metal shells. Lobster optics are thin glass plates. This makes the satellite lighter, allowing it to spin around faster to catch fading bursts. And coming up in 2025 is the SMILE mission, a collaboration between the European Space Agency and China. SMILE will turn the Lobster-Eye toward a much closer target, Earth. Specifically, it will look at the Earth's magnetosphere. We usually think of space as empty, but the Earth sits inside a magnetic bubble that is constantly being hammered by the solar wind. When the solar wind hits our magnetic field, it creates X-rays. SMILE will use a Lobster-Eye camera to take video of the Earth's magnetic nose, showing us the global weather of our magnetic shield as it buckles and flexes during solar storms. The wide field of view is essential here because the magnetosphere is huge, covering a massive portion of the sky from the satellite's perspective. We are moving from an era of pointing and looking to an era of monitoring and alerting. There are even concepts for the future, like the ISS Lobster, that would mount these modules on the International Space Station. Some scientists dream of arrays of these telescopes that could essentially film the entire X-ray sky continuously, creating a movie of the high-energy universe rather than static snapshots. It is humbling to think about the timeline of this technology. Nature needed about 500 million years to evolve the lobster's eye, perfecting a design that could see in the dark depths of the ocean. It took humanity another 45 years, from Roger Angel's 1979 paper to the launch of the Einstein Probe, to understand that design, replicate it in glass and iridium, and launch it into orbit. The Lobster-Eye telescope is a triumph of biomimicry. It reminds us that sometimes the solutions to the most complex problems in astrophysics are not found in a computer simulation, but are already solved, walking around on the seafloor. As these new telescopes open their compound eyes, we are about to see the universe as the lobster sees its world, a place where nothing can hide in the dark, and every flash of motion is instantly seen. The hunt is on. Thanks for listening to G Fun Facts Online.